but and MPI mainly. And it's also about non-volatile memory and modeling.
Okay. Thank you, Sophia, for the introduction, and thank you all for being here. Like Sophia said, this is another talk on non-volatile memory, so let me dive in and give you a quick introduction just in case you joined us for this talk. Traditionally, the storage in our computers is divided into two categories. On the one hand, we have the RAM, the random access memory, which is fast to access, to read and write, but it is, of course, volatile, in a sense that if there is a crash, there is a power failure, the contents of your RAM will be lost once you restart your machine. On the other hand, we have the hard disk, which is slower to access by comparison, but it is persistent, and it preserves its contents across power failures. And essentially, non-volatile memory, or NVM for short, is a hybrid of these two worlds, bringing you the best of both. It is fast and it is persistent. And in fact, it is becoming more and more prevalent to the degree that recently Intel, who are traditionally CPU vendors, have looked into manufacturing their own line of NVM technology. And in fact, earlier this year, they released their own NVM technology called Optane 3D. From our point of view in formal verification, we are interested in understanding the behavior of programs in this new context of NVM. So we know intuitively in the traditional volatile setting, if I have a program like this and I assign 1 to memory location X, if initially the value of X is 0, afterwards X will hold value 1. And of course, if there is a failure, once I restart the machine, there will be no way to recover this data, my work will be lost, and I will observe 0. By contrast, in NVM, if the same thing happens, once you restart the machine, so long as you have an appropriate recovery mechanism, you can see the work you've done before and, in fact, recover your work of X is 1. And of course, these are all intuitive behaviors that we expect, but we want to formalize these and describe them by formal specification. In fact, we want to go one step further and talk about the behavior of concurrent programs in this NVM context. But to understand what it means to specify the behavior of concurrent programs in this new context, we need to go through a history lesson very quickly. So it all started in the 40s, computation, with Alan Turing, who proposed Turing machines as a sequential model of computation, which was relatively simple. Then at some point we realized that if we want to harness the full potential of our rapidly evolving technology, we need more sophisticated models of computations, concurrent models of computations with multiple threads. And this is where the Turing Award winner Leslie Lamport presented the sequential consistency model, or SC for short. And he said, if you have a concurrent program, its overall behavior can be described in terms of an interleaving of the operations in each thread. So essentially, you have this total execution order prescribing the program behavior. And as intuitive and simple as SC is, it's actually not realistic. In fact, no existing hardware out there provides you with SC by default. So this is when researchers such as Peter Sewell in Cambridge University decided to look into more sophisticated concurrency models, collectively known as weak memory consistency, which are more realistic. And essentially, weak memory consistency says that forget about this total execution order because it's not realistic. So since you no longer can rely on this total execution order, you should expect to observe anomalies and weak behaviors that are not otherwise possible under SC. And this can be caused, for instance, because of instruction reordering by your compiler. And since we no longer have this total execution order to describe their behavior, we usually use something called a consistency model. And a consistency model essentially tells you the order in which the write operations in each thread become visible to other threads. There are several consistency models out there, both at the hardware level and the software level. In particular, we have the ARMv8 model of the ARM architecture. Now, what I want to do in the next couple of minutes is to convince you that understanding the behavior of concurrent programs in the NVM context is one layer of complexity above everything else we have seen so far. So to convince you, let me show you a simple example. So here, let's forget about concurrency for a minute, and I have a sequential program. I have a sequential program with two memory locations, X and Y. They're both initially 0, then my program executes, assigns 1 to them, and then it crashes. And I restart the machine, run the recovery, and now I want to know what are the possible observable behaviors. So one possibility is that I get lucky, I recover all of my work, and I observe that X and Y are both 1. But it's also possible to lose all of my work and see that X and Y have their initial 0 value. Now you might be thinking, hang on a minute. I thought the whole point was that I'm using NVM. Things will have to persist. So how come I can lose my work? And the answer to that question is that for performance, where every time you write to a memory location, it persists asynchronously. It means that when you write to a memory location, the execution doesn't have to wait for that write to become persistent. So it can go ahead, and at some future point, its writes will become persistent to NVM. And as a result, if you're unlucky enough that you crashed before either of these writes were persisted to memory, you can observe the 0-0 behavior. And for the same reason, if you crashed after the first write to X was persisted but not the second one, you can observe this 1-0 behavior. But most surprisingly, you could also observe them out of order. It's possible for you to restart the machine and observe the second write to Y, but not the first one. So this is called a relaxed kind of persist. And even if during the normal execution your hardware doesn't allow these writes to be observed out of order, for instance on the Intel architecture, it's still possible to observe them out of order once you restart your machine. So we talked about consistency models and how they describe the order in which the writes become visible to other threads. And the analog of that here is something called a persistency model, which describes the order in which your writes are persisted to memory. And whenever we talk about NVM semantics, the behavior of programs in the context of NVM, we really talk about both the consistency model and the persistency. So the consistency describes the behavior of normal executions, the persistency describes the behavior of the program after a crash, and together they describe the overall program behavior. So hopefully now you will see why this is one layer of complexity above everything else. Because not only you have to worry about all those issues associated with those weak consistency models, but you also have to worry about the persistency model and how these two interact with each other. In this talk, I'm going to present the PARMv8 model, the persistent ARMv8 model, which is essentially a formal description of the NVM semantics of the ARM architecture. And of course, this is a complex model. I won't be able to show you all possible behaviors, but I want to show you a couple of interesting examples of the ARM architecture. So let me go back to my running example, my favorite from before. And let's go back to those two abnormal behaviors that we want to rule out. So let's start with these relaxed persists, where we observe these writes out of order. So the existing literature, and I think one of the solutions in the existing literature to this problem is an instruction called a persistent barrier. And essentially, a persistent barrier says that, okay, in this example, if I put a persistent barrier between these two writes, it says that everything before this barrier, in this example, x is 1, should persist before everything after. So x is equal to 1 should persist before y is equal to 1, and as a result, you should never be able to observe this out-of-order persist behavior. And there are hypothetical models out there that propose such instructions, but they're very expensive to implement, and they're not currently available on ARM. ARM does not provide such persistent barriers. There are several memory barriers varying in strength from weak to strong, but they do not enforce any persist orderings in the way that we would like. So it seems like this problem is not solvable on its own. The second challenge that we talked about was this asynchronous behaviors, where it's possible for you to lose all of your work. And again, the answer in the existing literature is through these instructions called explicit persist. And in fact, you heard about this in talks, these flush instructions. So essentially what I could do here is that I could put this persist x instruction here that says, all right, when you're about to execute this, wait until all of the earlier writes, in this example x is equal to 1, become persisted to memory, and only then move on. So these are synchronous. Now it forces you to wait. And as a result, you can eliminate this x0, y0 behavior. And ARM's answer to these explicit persists is an instruction called DCC-wrap. Never mind that it has an odd name. But essentially, when I call DCC-wrap on X, it says flush or persist the cache line that contains X to persist to NVM. But it does so asynchronously, which means that when I execute this DCC-wrap X, I don't necessarily say wait until the persists are complete. And for that exact reason, I run into the same problem, so I can still see that 0-0 behavior. Is there a question? You're talking about the file system sync, fsync? Yes. Async, but fsync is global, whereas these ones are per cache line. Yes. Yes, yes. So because these persist instructions themselves are asynchronous, you can't manage to get rid of those asynchronous behaviors that we saw. Now, I've shown you two challenges, and all I've told you so far is that they can't be solved under ARM. Now, is this a pipe dream? The answer is no. And in fact, ARM allows you to solve both of these problems at once using something we call a persist sequence. Essentially, what ARM says is that, okay, in this program, if I insert this sequence here, a DCC wrap of X, followed by a full memory barrier, a data synchronization barrier in the strongest possible mode, then I can get rid of both of these behaviors. In particular, what this ensures is that first, this sequence makes sure this is now executed synchronously. So it will wait for all existing writes on X, all earlier writes on X to be persisted to memory. So they are synchronous now. We can get rid of that behavior. But it also disallows any reordering before or after it. So you also get rid of this out of order persist. Now, to formalize these and other behaviors of the ARM MVM semantics, we had to look at the ARM reference manual, which is 6,000 plus pages. And it's all in beautiful English, full of ambiguities, which we had to discuss with engineers at ARM to clarify their meanings. And after doing that, we arrived at a beautiful, concise, axiomatic specification of the NVM semantics. I've put it up there not because I expect you to read it or understand it. I'm not going to explain it. Just wanted to show you that it is quite concise, and it is an extension of the existing ARMv8 consistency model. So, okay, now we might say, all right, we now understand how ARM persistency works, so we should be able to write correct persistent code on top of it. But this is the wrong way to go, because we can't expect programmers to write this low-level code at the level of assembly, at the level of hardware. Traditionally, what we do is that we design high-level libraries, such as the durable sets that you saw before, or other ones that would make it easier for us to write correct persistent programs. And this is what we did in the second part of the paper. We devised a transactional persistency model, persistency library that would hopefully make it easier to write correct persistent code. And this is what I'm going to talk about now. So when we say transactions, we typically describe two behaviors. First, atomicity, and second, consistency. So the atomicity essentially says that your transactions have this all or nothing behavior with respect to writes. So if initially x and y are both 0, and I run this transaction, assigning 1 to both of them, at any point during the execution of this transaction, I see either the state before or the state after, but never an in-between state. For instance, I can never see x is 1 and y is 0. So this is executed atomically with respect to writes. But we also talk about consistency guarantees when there are multiple transactions running concurrently in parallel, and there are several consistency models out there for transactions varying from very weak to strong, one of the famous ones being serializability. So now we want to extend this concept of transactions to the persistent world. So the first thing we want to do is to extend this all or nothing behavior with respect to writes also to persist, which essentially says that when I write my transaction, if there is a crash at any point during this execution, once I restart the machine, I should either see the state before or the state after, but never a state in between. And second, we have consistency, but we also have seen that there is an analog to that called persistency, so we want to make sure we have correct persistency guarantees. And here is when we devised our own persistency model called persistent serializability, or PSER for short. So to understand what persistent serializability, let me quickly tell you what serializability is. So serializability says when you have multiple transactions running concurrently, no matter how they're interleaved, it appears as if they're executed one after the other in some sequential serial order. So in this example, I know that either T1 executes before T2 or T2 executes before T1. So they never interleave, really. Now, persistent serializability extends this and says, okay, as well as all of those guarantees, if the execution of your concurrent transactions crashes, once you restart your machine, you will observe a prefix of all the transactions that were, a prefix of the same total order of the transactions that were executed. Why a prefix? Again, because we want to allow asynchronous transactional commits. So you don't have to persist everything as you go along. So in this example, assuming that T1 was executed before T2, we know that either the crash occurred before both of them, so my prefix is empty, and as a result, I don't see the effect of either of them. The x and y are both still 0. Or the crash occurred in between, my prefix is only T1, I see the effect of T1, but not T2. Or the crash happened after both of them, my prefix is the full prefix, and I see the effect of both transactions. But what I can't see is a situation in which I see the effect of T2, but not T1. And in the general case, when you have n transactions running in parallel in this serial sequential order, I know that there is a point at which the crash occurred. Before then, all the transactions persisted, and afterwards, none of them persisted. And in fact, I can go one step further and say that, okay, I want to generalize this to multiple crashes, because essentially I can run my program, run into a crash and restart and run the recovery, run it again until the next crash, recover, and so on until I finish execution and get no more crashes. And persistent serializability says that, okay, in each one of these execution followed by recovery segments, which we call an era, you should be able to observe a prefix of the total execution order. Now, hopefully you'll agree with me that persistent serializability, or PSER, is strong. It's a simple model with relatively strong guarantees similar to serializability. So, but okay, is it any good actually? In particular, is it, I don't know why this is delayed, is it feasible? Can it be implemented? And is it useful? How can it be used by programmers? What can it offer to them? To answer the first question, we looked at implementing PSER on top of existing hardware. And since we had so conveniently specified the MVM semantics of the ARM architecture, we decided to implement it on top of ARM. And essentially what we did, we said, okay, pick your favorite serializability implementation, in our case, the two-phase lock-in implementation, and add some code to make sure you are persisting things correctly. In our case, it meant ensuring that we insert these persist sequences at the appropriate places. And the second thing we had to do was to add some code to log some metadata for tracking the progress of each of the transactions, so that if we crash and we restart, we can recover correctly. And finally, we added a recovery mechanism that said, okay, when your program crashes and you restart, check your log, check the metadata you'd recorded, and check the progress of each of the transactions. Now, depending on their progress, either complete their effect, roll the transactions forward, or roll them back. So in essence, by doing this, you make sure that no transaction is in this limbo intermediate state, and you see all the effects. So to answer this first question, is PSER feasible? The answer is yes, because we have managed to implement it on existing hardware. And in essence, we have shown some compilation results from PSER to ARMv8, and we have a formal proof saying that this compilation is correct. To answer the second question, is it useful, we did the following. We said, okay, let's say you have a library, for instance, a Q library with two operations and an NQ and a DQ. And let's say you have a sequential implementation of this Q library. Now take this sequential implementation and wrap each one of its operations inside a PSER transaction. Now, if your sequential implementation is correct, then by wrapping each operation inside one of these transactions, what you get is a correct, concurrent, and persistent implementation of the same library. Now, what do I mean by this sequential implementation being correct? I mean that it has to be reasonable. For instance, if I have a Q implementation where the DQ always returns value 7, I can't magically make it correct by wrapping it inside a transaction. So in the Q case, it means that your sequential executions, your sequential traces, need to satisfy this Q FIFO property, the first in, first out property. And if that's the case, by wrapping each operation inside a transaction, what you get is a concurrent and persistent implementation for free. So we think the answer to this question is yes, because essentially we are giving a way to programmers to convert their sequential implementations into a persistent one for free. And that brings me to the end of the talk. I've shown you the ARMv8 model, I've shown you the PSER model, and there is a little bit more in the paper. In fact, we have presented a general framework for describing persistency models, and indeed we have presented ARMv8 and PSER as instances of this framework. So feel free to go and have a look. And in terms of future work, there is quite a bit to be done in this, in the domain of NVM. In particular, from the verification point, we are interested in other reasoning techniques such as program logics or model checking algorithms. And some of that work has already started, so stay tuned. And with that, I would like to thank you all for being a great audience.
Can you please queue for questions? So I'll start by asking, can you speculate what it would take on this architecture to implement the lock-free set algorithm that we saw earlier?
So essentially, these flush instructions that you're talking about, you could replace them with this DCC wrap or the persist instruction in ARM, but you will essentially need to insert these persist barriers to make sure that they actually flush, so that because like you saw, these persist instructions are asynchronous. It doesn't necessarily mean they are flush.
This you certainly can do, but I was hoping there would be something more efficient.
I can't comment on that without actually understanding the particulars of the implementation, but yeah.
Hi, thanks for the talk.
Okay.
In your discussions with the ARM engineers, did they discuss like updating the semantics of the flush instruction to like imply a full barrier? That seems sort of, I guess, intuitive, unless I missed something. So
we did actually push them because it would have been a lot nicer from the programming perspective to have these global barriers, but they were very resistant because it is very expensive to implement. It's also quite hard to implement because essentially your implementation needs to keep track of all the dirty locations, as it were, the locations that haven't persisted yet, track them at all times to make sure they're all persisted when you put a barrier. So far, they've told us no, but who knows?
I have one more question, if that's okay.
Yeah.
So presumably with the transactions, you're getting kind of an either or, and there's one other possible outcome there that seemed at least semi-reasonable, which is like the first write. In your example, the first write, I believe, is X first and then Y. Do you think in practice there's a performance benefit to basically allowing that to happen, or do you think just in transactions?
Potentially there is, but then you don't have a transaction. I mean, it depends on what you want out of a transaction. In most transactions, unless they're very, very weak, you get this atomicity of writes. So,
is there a lot of use? Like, is there somewhere you can go to look to see what like common programming patterns are? That's why I ask.
I don't know about common programming patterns, but so one promising thing is that, for instance, Intel has this PMDK project, Persistent Memory Development Kit, and they provide several libraries, and they have a very similar transactional library. So if they are doing it this way, but providing atomicity, I think we're on the right track.